Today, Professor Mutlu isn't in town, so I'll be giving a lecture on virtual memory. And the slides will be from, I'm going to borrow like material from Honor and also like previous TA Justin Mesa and Yoongu Kim. And I have some announcement. Lab 3 is due next Friday, actually. I was like, no. the date is right, Friday 21st. But that is Friday. Homework 3 is out. It's going to be about the same length as the homework 2. So be prepared that it's going to be a little long. But it should be a good practice for a midterm, which will come a week after that. And another like minor announcement is next week, as I promised you guys that I'll be doing a conclusion on some of those, most of the required paper and present it during the recitation, which is the lab section. So I'm going to distribute it to all the TAs that we have. And Varun is going to cover all of those on Tuesday lab. I'll do the Thursday lab, and then either Paraj or Xiao will do the Friday lab. So if you haven't done the reading, or you would like to get a conclusion on what those reading goals and what are the problems they are trying to tackle and what are the major findings, please attend the recitation. Great, yeah.
We should be able to make a Piazza post about that.
I will. And the other thing is for those who haven't handed in the diagram for Lab 2, I'm going to make a Lab 2 diagram folder in the hand-in folder because right now the Lab 2 folder is locked, so no one can actually put anything into the Lab 2 folder. I'm going to make another separate folder so I can submit the diagram. And for the checkoff, please make sure you have the diagram ready, either opening up on your laptop or have it printed out. And today, Friday, will be, I guess, the last day that we can do the checkoff, unless you have a major reason why you cannot make it this week for Lab 2. And we'll try to grade Lab 2 as fast as possible, and we'll send you guys a feedback on what particular cases or tests that you fail, so that you can make sure for Lab 3 it doesn't get propagated to the same errors again. And so you can focus on the pipelining part of the Lab 3. All right, so let's go over the virtual memory and what are the problems of using just the physical memory. In the programmer's point of view, when you program something and you would like to use a memory, here's what the programmer sees. When you are writing something in assembly or something in the C code, when you deal with memory, you do one of the two things. You store some data in the memory and use that later, or write them in a file. Or you can load some data from a file or some location in memory and get that data so that you can do some computation later. And ideally, what we want for this memory to be is we would like them to have a zero access time, which means whenever we want to grab this particular data from memory, it should arrive right away. It should have infinite capacity, which means that we can store as much data as we want at any time, and we will never run out of memory. And should be zero cost. Ideally, I wouldn't like to buy a lot of DRAM for my machine. And lastly, I would like to have the memory to have infinite bandwidth so that I can support multiple accesses in parallel. For example, if I have a parallel code and I would like to access 10 memory locations at the same time, I should be able to do that. But as you guys can imagine, what these are ideal and are not true in the real world, because memory incurs some cost. The faster one, they are more costly, and also smaller, as in you cannot have 1 gigabyte of SRAM because they are too costly comparing to DRAM. And here's how the modern memory hierarchy looks like. You have the tiny amount of register files, which is the fastest memory. On most machines, this spans 16 or 32 entries, that can store a word. So in all, you can store 32 words. And the access latency for this register file is usually, say, 1 cycle or sub nanosecond. And in addition to that, these register files can be managed manually through either through the compiler or you just write your assembly code that deal with how you're going to manage all these register files. After these layers, you have several layers of caching, which is a fast memory. These are SRAM cells that are tiny but are faster than the usual DRAM DIMMs that you can buy from, say, Newegg. And after that, you have the actual main memory, which is the DRAM. And the size of the memory is typically in the gigabyte. So if your program, for example, operates on a terabyte of data, somehow you would like to make sure that virtually it can deal with all that terabyte of data with the latency or the access latency of around like 100 nanoseconds instead of having to access the disk, which are a lot more slower than the main memory. And without the virtual memory, these are the example of how you can lay out different addresses and how can you handle the access from the program. And can you guys give me some example of what are the potential problems of this model without the virtual memory? Yeah.
Like some program can override another program's memory location?
Yeah, so security is one of the major problems because you have no way to control what particular segment of this different pages that a particular process can access. So you can have 3 processes that doesn't have anything to do with each other trying to access the same location in memory, and then it causes either malicious activity to the systems or it just cause fault and just render your system useless or crash. What are the other potential problems that can occur in this particular setup? Yeah.
You can only run a finite amount of programs. Once your physical memory is done, like you start overlapping.
Yes, and in addition to that, there's another problem called segmentation, and I'll show you what it means. For example, you have a program 1 and here's the memory. And this is a contiguous memory at the initialized state, so everything is free right now. And program 1 accesses, say, 4 blocks of memory. And then it performs some computation. And later say, oh, I don't really use this particular chunk of the memory anymore, so I free this. And as you can see now, you have like segmented memory. Even though these 3 segments combined are enough that another program, say, you want to use this much memory space, because it's segmented now, how are you going to allocate that particular block to the other processes? So this problem is called segmentation. And virtual memory, which provide indirection, can solve this problem as well. And then lastly, what are the, it's a simple problem, but what are the other potential problems that can happen in here, in this case? Well, what are the ideal memory that we would like to have? We would like to have an infinite amount of capacity, right? So, but when you buy the memory, the DIMMs from a retailer, you don't have that. You say you buy a 4 gigabyte DIMMs and you plug it into your machine. Now your machine has only 4 gigabyte of main memory, but you would like to virtually make the program realize that, oh, I actually can access more than 4 gigabytes. I can actually use 1 terabyte of data, and somehow there'll be a management unit that manage this virtual memory space and making sure I can run my program as if I have 1 terabyte of memory. So I'll list again what are the potential problems. First of all is physical memory has a limited size. And the bigger the size that you would like the system to have, the more costlier your system is. And what if you just need close to infinite memory? You can potentially buy a system with like terabyte of memory, but that would cost a lot like of money, probably more than like thousands of dollars. And the second concern is, should the programmer be concerned about the size of memory at all? Like whether I initiate this block of memory, should I be concerned about whether it's going to use more than the amount of the physical memory that I have or not? And then the next question is, should the programmer, the high-level programmer that just want to program their application, manage the data movement from disk to the physical memory? Because that's another complicated algorithm that you have to perform in addition to just writing your own program. And the answer to this two problems is probably not. If I'm just want to write a program in Java, I probably don't want to like deal with all these issues. Also, in addition to this, ISA can have address space that are way greater than the physical memory size. Say, all of the machine that you have right now probably use 64-bit address space. Those are way more than the 8 GB memory that you have on your machine. So it's the job of the management unit that manage the virtual memory to handle all these issues. So the basic mechanism of virtual memory is to provide some indirection. And what does it mean by indirection is address that are generated by each program or each instructions in the program is called virtual address. And this virtual address is not really the address that you would like to use to actually access the data in your memory. And this virtual address is linear in the programmer point of view. So you can go through the virtual address in a linear manner. There's no segmentation within the virtual address space. And then you have the address translation layers. And if you took 213, and I guess most of you taken 213, right? Yeah, it's required. I mean, that may be some master students that might not take in this. That's why I'm going over this again. That's another additional address translation layer that manages the indirection and maps the virtual address into the physical address, so you can actually locate where my data is in the actual physical memory. And this address translation layers is being managed by a unit called MMU, which is a memory management unit. And this layer is being implemented in the hardware and software together. So it is called a hardware-software cooperated mechanism that you have some hardware that deals with the interaction and having this table, and then the software program how are you going to define the interaction and mapping from the virtual address to the physical address. And here's one high-level example of a machine with the virtual memory, which is most of the machine, probably all the machine that you use right now. You have a CPU, and then you have the memory. Those two units are similar to the machine with physical memory. But then you have these interaction layers that translate the virtual address using what we would call the page table, which is simply a table that you can use the virtual address to look up where in this memory space is actually the physical page that you would like to access. And this page table helps translating the virtual address into the physical address. And as you can see, there can be two cases that can occur in these scenarios. First of all, if you would like to access some page in the memory, and the page table say, oh, it's over here in the memory, everything's fine. You just grab that page and process the data. But what if you would like to access this particular page which doesn't exist in memory? This is something we call page fault. And If that's the case, you have to grab the data from the disk and replace some page in the memory. And the address translation layer, first of all, it converts the virtual address into the physical address. And then the memory management units also handles how the mapping, also how you're going to replace page in the memory with the one from the disk when you fetch one. And now I'm going to go over some key terms that we will use in this class and in general. So when we refer to pages, it means that you have a virtual address space, which is a contiguous linear space that each of the program sees. This virtual address space is divided into pages. But then if you refer to a frame, now you're looking at the physical memory that you have in your machine, and then the physical address space is divided into frames. So there are pages that are associated with the virtual world of each program, and there are frames that are actually the physical memory that you have on your machine. And then a virtual page is mapped into a physical frame. And in this case, we assume that a page is in memory because the frame are the physical addresses that lies in the memory. And then if you access the virtual page that is not in memory, but they are on the disk, virtual memory systems has to bring the page into the physical frame, and we will call that a demand paging. And then the page table, as I described earlier, is the table that stores the mapping of this virtual page into the physical frame. And now the next question is, what do we need in order to support VMs? Any ideas? Like how, yeah.
Well, you need a hardware translator, probably that sits in between the memory and the CPU.
Yes. So first of all, you need the hardware component, which we would call the MMU, that handles how you're going to translate the virtual address to the physical address. And then there are a lot of jobs for the software to leverage the MMU. In particular, they have to first populate the directories and the page table, which means that they have to define some mapping from the virtual address to the physical address. And then whenever you have a context switch, you have to modify the page directory, the base register, so that you point to the correct page directory. And as some of you pointed out, you can have some security issues, and virtual memory can help supporting or protecting against these security issues. So one of the jobs that the software layer has to help the MMUs to set the correct permission for each of the processes, and we will go over this in the next lecture. And also, lastly, what did you have page fault? You have to define a way to manage the page fault. Also define like which pages inside the physical memory you would like to replace, because you would like to replace the one that would affect the system performance the least. And these are the additional jobs from the software side that we are not going to cover that in this class, but I would like to go talk about them a little bit so that you're aware of how many jobs that the software has to manage in order for the MMU to not only be functionally correct, but performs well. It has to keep track of which physical pages are free, and it also has to allocate the free physical pages to virtual pages. And then you have to make sure you replace the page that would have the least performance impact to the systems. And how are you going to handle like sharing between processes when they have shared address? And these two are additional techniques that you can do in order to get better performance out of your system, which is copy and write optimization and also the page flip optimization. And now I'm going to give you another example of what would happen when you have a page fault, which is you would like to access some page in a physical memory, but they're not there. And it's a job of the memory management unit to handle this case in order to pretty much to grab the data from the disk and get it to the CPU that requests this page. So before the page fault, you have the CPU, page table, and memory, and you would like to access this particular page, but they're not in the memory. First of all, you have to grab the location of the page, the physical page in the page table, and this page table will have a valid bit saying whether it's in the memory or not. In this case, they're not in memory, so you have to grab them from this. You have to generate first the page fault exception, and then OS will have a trap handler, and this is now in the software layer that invoke movement of data from the disk back to the memory. So after the fault, this particular page are now located somewhere in the memory, and you can access the page. Yeah.
So just to clarify, the MMU doesn't do any of that. It just tells the OS that there is no.
So MMU throws the exception. OS define how you would like to handle the page fault.
And then it tries again.
Yeah, and can you guys give one example of what's the benefit of letting the OS handle this page fault? Yeah.
Well, maybe like the OS knows exactly what all of memory should be used for.
Yeah.
So maybe it can choose how much to copy into memory. It can copy like a little bit, or if it'll be using a lot of that, it can copy the whole thing into memory or something.
So you're talking about, say, you prefetch more data into the memory in case you would like to use them in the future?
Yeah, like if you get a fault
Yeah.
for like a specific address and
Yeah.
you know what program it's coming from,
Yeah.
you have to decide whether you just copy that like word or whether you're copying maybe 10 words.
Oh, so in general, you actually copy the whole page.
Oh, okay.
Yeah, so that's usually the case. But you can actually copy more than that if you know that you have a program that loops. So you have a for loop that accesses a lot of data that spans, say, 4 pages. And somehow the OS see that pattern and knows that, oh, I will probably use the next 3 pages again. So one optimization you can do is which would be called prefetch, and it's commonly done in the more on the DRAM. But you fetch those data ahead of time because you're almost sure that you're likely to access them, so you don't incur 4 page fault. So in that case, you will incur 1 page fault. Yeah, and I think you was okay. Yeah.
Can you then define more clearly what a page is? Is it like all 32, like all, like an instance of all of memory, or is it a section of memory?
Oh, it's a section of memory. It's a block of memory. So for each machine, the page size is defined to be, say, for example, 4 kilobytes or something bigger than that. It's up to the different machine how they define the page size, and there are trade-offs. If you have a bigger page, then you can. One thing that can be disadvantageous is you wasted bandwidth. It's possible you wasted bandwidth because you fetch, say, 4 megabytes of data, but you actually use 4 kilobytes of them. Now you wasted a lot of bandwidth. But then what if you have tiny pages? Now you have to have a lot of bookkeeping or keep track of all the pages. So there's that trade-off between small pages and large pages. And we're going to cover that a little bit later in the slides.
But it only has, like physical memory only holds whole pages. It doesn't hold partial pages.
Yes.
Okay.
The other things that the OS has to handle is which across all the pages that are already in memory, which one you would like to evict. For example, what if you have no more free pages, but then you would like to get a page in the disk? You cannot just put them in here because they are not free. It's the job of the OS to figure out which page in the memory that you would like to evict, because if you evict the one that would be used soon in the future, you're going to incur a page fault again. And that's a lot of latency you have to wait for, because the latency from getting the data in the disk is really, really high comparing to the memory. It's like order of magnitude higher. So you would like to minimize number of page fault. In that case, one way you can do is you predict which block in the memory would be used the least, or would probably never be used again, and you evict that from the memory and then swap them with the one that you would like to access. So in order to service a page fault, I'm going to have a separate diagram that shows the processor, the memory I/O bus that connects the memory and a peripheral on your system that would be called the I/O controller that connects the disk to the memory. So whenever you have a page fault, the processor signals the controller saying, oh, I have a page fault. I would like to read a block of length, say P, at this address X, and store them in the memory address Y. So first of all, the processor initiates the block read to the I/O controller. I/O controller read that block from the disk, and then the read occurs. And these data from the disk would be transferred from the I/O controller into the memory I/O bus, and then from the memory I/O bus into the memory through the direct memory access. So what I mean by direct memory access, you don't have to go through like the processor to access the memory. And this is under the control of I/O controller. So you, in this particular process, in some sense, you copy the data from the disk, move them into memory so that it can be used from memory. And then afterward, after you're done copying the data from the memory, from the disk into the memory, the controller signals, the I/O controller signal completion, saying, oh, I'm done. And then it interrupts the processor, and then OS can resume the process as if it's suspended because of this page fault. But what if you just run out of memory? What if you have a program that keeps using all your memory, and then you have another program that you would like to use, but you're running on memory, you would like to access them? This can be called page swap. It happens when you're running on memory program. How many of you just run, for example, Linux machine, and then run some program that keep using memory more and more and more? At some point, your machine slows down significantly to the point you can barely type in anything, but it's still running. Yeah. So many of you have done this before. And I've done this before too. Somehow I write program and I accidentally have memory leaks. So my program keep using memory, and then I'm trying to type like Vim so that I can edit another program. I can barely use Vim. And usually, in most cases, what happens in this scenario is you're running on memory, and you have you incur something called page swap. What happened here is you have a physical page that are being swapped out to the disk. And as I mentioned earlier, when you access something in the disk, it's order of magnitude slower than accessing anything in the memory. So in this case, a lot of your data are being migrated from the physical page into the disk. And this free up those physical page. And as a result, the page table entry become invalid. And then you brought the other page back into the memory. However, because you have two processes running, what happened is I have a process that has, say, memory leaks that keep using memory. I have another process I'm actively using. I'm typing something in Vim. They have to use some memory. This process say, I will get more memory. I will access something. And oh, they're not in the memory anymore because it gets swapped out. So I have to access something in the disk. And you grab that data, put it back in the memory. You swap other things that are likely to be my Vim process that has some data on the disk. And now it got swapped back out to memory. And you have this ping-ponging effects between two processes that try to grab the data, but most of the time they are in the disk because you had a lot of memory footprint. and your performance, your machine slow down significantly to the point you can barely do anything. And this is called page swapping, which is a ping-ponging effect between different processes. Now I'm going to go into how you do the address translation, which is another important topic in virtual memory. So for this topic, I'm going to explain how can you get physical address from the virtual address. And I guess because you guys have taken 213 before, most of you probably went over this like many times in 213, including 213 exam. And yeah, I see some laugh. So the page size, as I told you, is specified by the ISA. So different machines have different page size. The VAX has 512 bytes. Today, modern machine, this can range from 4 kilobytes, 8 kilobytes, 2 gigabytes. That is a little large, but it's possible. You can have like small and large pages mixed together as well. What are the trade-offs between big and small page size? I'm going to go over that in the next slide. And in addition to that, what are in the page table? The page table, first of all, has to somehow store the information that where is this particular memory address is mapped in the physical address in the memory. And each of those entries is called page table entry. And then I'm going to go over what is actually in the page table entry. But first, let me go over what are the trade-offs between different page size. If you have a large page size, the benefit is you don't really need that many page table entries. And you can save memory space because you don't really need those entries. And then, in addition to that, there can be fewer TLB misses, which I'll go over TLB later in the next lecture, I believe, which is another optimization on how can you grab the memory fast. But keep in mind that if you have a large page size, you can have fewer TLB misses. And what are the disadvantages of large page size? Anyone would like to? Yeah.
So fewer pages fit in your physical memory, so it's
Yeah.
probably easier to get thrashing if you run like many programs at the same time.
Yes, that's possible. If you have an access pattern that touch, say, page number 1
Yeah.
a little bit, then touch the page 2 a little bit. So you have a lot of, you can first of all cause thrashing, and it's inefficient because you fetch a lot of data from the memory, but you use tiny amount of bit. So it can cause extra transfer to and from the disk. This wastes a lot of bandwidth and also reduce performance. And in addition to that, it can large page size can cause internal fragmentation, which means that, say, I want 1 kilobyte, but somehow my page size is 1 gigabyte, so I have to allocate 1 gigabyte. It's a waste of space, and I kind of went over external fragmentation earlier, which is when you have segmented address between processes, and you don't have enough space for the other process to initiate memory. And lastly, you cannot have any fine-grained permission, because every page size is 1 gigabyte. If you want to, say, let process 1 use this particular page, how are you going to do finer grain permission handling in this case? Now, on to the address translation. I'm going to define some parameters that we use often in this class. And I think it's pretty common in other classes as well. P will refer to the page size, and the small p would be the bit, how many bits is used in order to refer to the page size, and the page size would be 2 to the small p. And n would be the virtual address limit or the virtual address space, and then the actual big N, the capital N, which is the actual virtual address, would be denoted into the form of 2 to the n, which is number of bits to refer to the virtual address. And then the small m would be the physical address limit, similarly to the virtual address, but this refers to the physical address. And given that when you have a virtual address, some parts of those bits would be used in order to refer where in the page table entries are those physical pages. And then some of those bits would be used for the offset. And in order to calculate that, suppose you know that your page size is, say, 2 to the 12 bytes. That means that your offset, which should be denoted in this form 2 to the p, the offset will be from bit 0 to bit p minus 1, because that's the amount of indexing that you need in order to, when you grab a page, you know which particular virtual address within that page that you will grab the data from. The next information that you need is where in the page table entries that you have to grab the actual physical page number from, because the page table entries stores the information of where that particular page is. In this case, because you know the virtual address size, you can infer that information and get the information what bits field within the virtual address is the virtual page number. And this will be from the bits field n-1 up to p. And the address translation layers, which has a page table entries, maps the virtual page number. So the virtual page number becomes the index. So suppose this is the page table entry. This would be the index, and this would be the actual page table, physical page number. You use the virtual page number to locate where in this table is the actual physical page number. Suppose this in this entry, you would have the virtual page number, and you would compare the virtual page number throughout this table to see whether it's matched or not. If it's matched, it means that this number is a physical page number. And then you concatenate the page offset, which is the same from the virtual address to the physical address, into this particular number. So this would be physical page number that we can get from this PTE table. And then you concatenate the page offset in order to get the actual physical address. And once you have the physical address, you know where exactly in the memory that you have to grab the data from. And note that the page offset bits is the same from the virtual address into the physical address. And the MMU, which handles the address translation, handles how you can transform the virtual page number into physical page number. So first of all, this address translation layer also separates each page table for each different processes. And then the virtual page number forms the index into the page table, which I described over here. The page table entries provide this information about where the pages are. So you have, normally you have, say for each of the process, you have the page table based register that tells where this table, this whole table is located at. And then you have the page table that lets you translate the virtual virtual page number into the physical page number. And then you concatenate that with the page offset to get the physical address. But there are other information that you need in the physical in the page table entry. And the reason for that is that you can handle some permission between different processes. And also you can handle whether it's a page fault or not. And if in order to handle whether you have a page fault or not, you have a valid bit. Whenever the data is no longer in the memory, this valid bit will be set to 0. So even though you have some entries in here, if this valid bit is 0, it means that you have page fault. So if this bit is set to 0 and you try to translate this physical page number and get the data from memory, it's not the data you would like to access anymore. And what you have to do in this case is you have page fault and you grab the data from disk, move it to memory, and then actually accessing that data in memory. And afterwards, suppose this valid bit is 1, you can access the physical address using the virtual page number, index into this table, get physical page number as I described earlier, concatenate the offset, and you get the physical address. And here's the bigger, higher level overview of how this process is done. You have the CPU chip. So everything here is within your CPU, the chip. And then you have the cache and the memory, which most of the case, the memory is off chip. So the latency is actually higher. If you have a page hit, first of all, you send the virtual address to the MMU. MMU translate that and get the physical address. And because the valid bit is 1, you get the physical address and grab the data from the cache and memory. But before that, let me ask you one question. Where does the page table entries is located?
Probably in the cache.
Yes, either that or in the memory. So in the next lecture, I'm going to talk about one optimization which is called the TLB, which cache this physical page table. Because if you look at how you search entries in here, if everything here is in the memory, you have to actually walk through all these indexes in order to find where this particular VPN is located at. And that can be a long process because you have to stress, like you have to compare all these indexes, and that can cause a lot of latency. So first of all, you get the page table entry and look it up in the cache or memory, depending on where that's located at. And then you grab the page table entry, translate the virtual address into the physical address. Go back to memory again, grab that particular physical address, physical memory, send the actual data back to the process so you can actually process the particular chunk of memory. However, what if you have page fault? Now, when you have a page fault, the whole process is more complicated because first, you have to send the virtual address to the MMU. MMU accesses the cache and all the memory in order to look up that table. And then when you look it up, say, oh, it's invalid. It's a page fault. I have to grab the data from the disk. So first of all, you have to send the page PT address to the cache, get the page table, send back to the MMU so that you can see where it's valid or invalid. And because it's invalid, MMU send an exception so that you can have the page fault handler that allows the I/O unit to access data to the disk. So when that happens, suppose the memory is full, the next thing you have to do is you have to evict something in your physical address, in physical memory, back to the disk. So in this process, GOS somehow specify which particular page you would like to evict them to the disk. And then you grab the page you would like to access, put them back in the cache. And now the handler will return, and because the new page is already in the memory, you can fetch that, send it back to the processor, and continue its own process. And as you can see, how many data, comparing to this case, how many data accesses in addition that you have to grab. In this case, first you have to grab some data from the MMU, from the cache into the MMU. So that's one, and that's accessing to the memory. So you have so page it. And this access to the memory. And this accessing to the disk. Okay. First of all, you have to grab the data from the cache or memory. So you have one page table entry is sent back to the MMU. And then you, okay. So the first one is not actually like sending anything. You just send the address to the memory. So you grab the data back, the data from memory. You send a physical address. You grab the actual data to the processor. So you have essentially two memory accesses to the memory or cache. In this case, you have the same process. You send the page table entry address. You grab the actual page table entry. So you have one memory access now. It's not valid. You send exception. You grab the page from the disk, and you also have to evict something from the memory into the disk. So you have two transfer from and to the disk. And then once you have that, you now can get the virtual address and do the same process in order to grab that particular page in the memory. So you have two additional memory requests or data transfer from to and from memory. So as you can see here, you have one additional memory access, two additional disk accesses. And as I said, the disk accesses is order of magnitude longer than the memory access. So whenever you have a page fault, you have to wait a really long time comparing to when you have a page hit. All right, let me take a break over here right now, and I'm going to cover like multi-level page table afterward. So what are the issues of, what are the possible issues that you have to think about when you design the virtual memory and this page table entry and memory management unit? Actually, let me erase this in case I have to use it later. First of all, how large is the page table? Because page table is stored in the memory, so it actually uses the memory space. If you have them too big, now you don't have space to store your actual data. And where do we store it? In hardware, in the physical memory, or in the virtual memory? It's also possible to store a page table in the virtual memory. And then, regarding that, where do we store it? How can we store it efficiently without requiring that physical memory can store all the page tables? One way you can tackle that, and also this is being implemented in many modern processors, is to use multi-level page table. Conceptually, they are the same as single-level page table, but now you have several interactions. So you can have more virtual address space without requiring multiple. It requires multiple page tables, but you don't require the same amount of space that you need in order to support that many virtual address space to store the page table. And in this case, only the first level page table has to be in the physical memory. The rest can be stored in the virtual memory. And the remaining, well, even though they are the rest of the level in the page table, even though they are in the virtual memory, they can be cached in the physical memory when they are being accessed so that it can be faster when you want to access them. Because if you have multiple levels, the first one is in the physical memory. What if the other one is in the disk? So in order to get the virtual address, you have to access multiple. You have to go multiple times to the disk in order to access that, and that can be really, really long. And this is one of the possible scenarios. You have a 64-bit machine, and you only want to use one level of page table entry. You have a VPN that are 52 bits long that contains the page table, and then you have the page offset, say 12 bits long. And suppose that this is your systems. How big would the page table be? That is 2 to the 52 entries multiplied by 4 bytes per each entry. And that is like 16 times 10 to the 15 bytes. And that's just for one process. And you have multiple processes on your machine. Obviously, this is not the scalable solution. You have something more scalable, and that's why you have to have, so that's why a lot of modern processor employs multi-level page table. And here's the high-level concept of multi-level page table, and this is done in the x86 ISA. You have the linear address space, which is your virtual memory, the one that your program or your processors see. And this is a contiguous block of memory. Each of these entries can be can be accessed, and each of the entry you have the directory, the table, and the offset. So this is the 2-level page table. The bit fields that specify directory is being used in order to grab where in within the virtual memory space is your page table that you would like to look at. So first of all, you look at the directory in order to get where the page table is. Afterward, you use the page table to index within the page table where is the page table entries that are located at in order to get the actual page in the physical memory. So this is the physical memory. And you append the offset with the page table entry to get the actual physical address. And this page mapping is used for 4 kilobyte pages. And the normal 32-bit physical address size. In the 64-bit machine, Intel x86 actually use 4 levels of indirection in order to access your page. So regarding that, in details, how do we actually access the page table? Right? So you have the virtual address. And this is the directory. This is for the page table. And this is for the page offset. And it's the virtual address. And in the end, what you want is your physical address. So first of all, the page offset is the same. So one thing you can do is you just move the page offset and wait for the rest of the information to be filled here, and that's your physical address. And the rest are being handled by the MMU. The first thing you need is where is the page table based register, which is this particular information. First of all, you have the directory that can be used to index where is the page table in the page directory. So you have the page directory. and then you grab this information, whatever number of bits they are supposed is, say 12 bits. You look it up in the index. You compare each of these entries in the index. If they match, it means that it matches with this one. It means that this particular entry you can use to append to this table in order to search where exactly is the page table entry. So you have the page table, which is a second level interaction. You have the index. Similarly to the page directory, you have the index. And also like the valid bit, yeah.
Is there any particular reason why they aren't ordered? Like why you have to have the index?
Oh, it's possible. You mean why do we need the index?
So that you don't have to look through it and try to match it, but just like, so once you know what the base is,
Yeah.
you like subtract that.
So first of all, you somehow you have to search whether the index match or not. So that's required because you have to know which entry in here
But
is.
that's what I'm saying. Like if you think about memory, yes, technically there is an implied index of 1 through whatever the maximum is.
Yes.
But you can address directly into it because of the address. So why can't you apply that same principle to this and have them ordered such that you don't have to look through all of them and compare?
So what if it becomes invalid, for example, and you have some other virtual address replace this?
So then what's the point of the valid bit?
The valid bit tells whether it's in or not inside that. But what if you replace that particular entry with something else?
Oh, so the valid bit is for when it starts off, they have to be zeroed out.
Yes. Well, or when you evict them, and you have nothing else to replace. Suppose I just do free, I malloc and do free.
Yeah.
Those things should be 0. But you don't really have to like write or like like zero out that entry. You just zero out the valid bit, because that's a lot simpler. Yeah. But like, what if you place this entry and the interaction changes?
Yeah.
Now you have to somehow manage the search, like make sure this is searchable. That's why you have to like walk through this table. Okay, so now you have to search through the index in the page table. And you grab this information, append this information. Look into this table. In order to get the physical page number, and then append it with this information to get the actual physical address. So in high level, this is almost similar to having one level page table entries, but you are able to just to have many more space, because this page directory allows you to have multiple page table. For each of the page table, you can use to index into multiple location in your address space. So this is a much more scalable solution. And you can imagine what if you have 64-bit address space. Now you can have multiple directories across the 64 bits, so you can have multiple level of interaction to get even more space. Yeah.
Do those entries provide virtual addresses or actual addresses?
Which
They're
one?
Like the page directory entry.
So it's not virtual or physical address space per se, but it provides you the next level of indexes.
But that's located somewhere.
It's located somewhere. So that depends on where you would like to put this information. So it's possible to put this outdoor table in the physical address. It's also possible to put them in the virtual address here. It depends on how you would like to manage this, and there are trade-offs. So you can put the remaining levels in the virtual memory, because the first level page, the one that you actually have to access the physical memory, that has to be in the physical memory. The rest can be in the virtual memory.
So is it possible to get deadlocks in terms of you're trying to get to this page table, but you need a page table to get to the page table?
But you need,
So if it's in virtual memory,
Yes.
you need some sort of table to get there.
so
But maybe that table is also virtual memory.
then you have, what if you have, so are you saying, what if you have multiple page fault when you,
What if you have a page fault when looking for the page table?
well, then you grab that page from the disk, and then that is in the memory, so you can access that particular data,
Yeah.
and then, oh, I have page fault again. You grab another particular data in the memory in order to access the next level, because this process is sequential. You can search for this first,
Yeah.
search for this later, and then search for this. So
But they can't like cross-reference each other.
well, I mean, you don't have to, for this table's entry, you don't have to cross-reference and refer anything, like get any information from here. So once you're done with this, you can, I mean, this is just like a tiny piece of information. Once you get this data, it's just a few bits, right? Once you grab the page directory, you only have to grab this data. So you can temporarily store this data, or actually you can do this in hardware, so depending on how you implement this. But there's like a tiny amount of memory, I mean, it's a few bits. Then you grab the next level, append this data to the virtual address, grab the index into the virtual memory, I mean physical memory, my bad, and then grab the actual data from the physical address. So it's possible to have multiple page fault, and hopefully that doesn't happen because OS should handle that and make sure you don't have many page fault when you try to look up some address. But there wouldn't be a deadlock. And these base register that you use to refer to the page directory is a part of the process context, similar to like PC or other register-based contexts that are involved for each of the processes. So this need to be loaded when you have context switch. So for example, if you are process number 1, you're done with whatever you're doing, and then somehow you get context switch, you move, you are now running process 2 on your machine. The base register that you use to access the page directory has to be changed. Or now you have a different base register, and you use that information to grab the data from the physical memory. So this is one of the examples of the real-world processor that use multiple levels of interaction. And for this particular case, you're looking at 32 bits x86 machine. Within that 32 bits in x86, the specification is the first 10 bits is for the directory, and that is used to look up the 20 bits information, and you can append with the next 10 bits to get the page table entry from the page table. And then the last 12 bits, because there is 4 kilobyte page, and log base 2 of 4K is 12 bits, so that's the offset of where exactly that physical address is, and you append the page, whatever you get from the page table entry to get a 32 bits physical address. What if you have 64 bits machine? Oh, let's go over this first. What if you have a 4 megabyte page using 32 bit paging? Because now your page is 4 megabytes, you don't have to have that many, you don't have to, the space required to store all the page table entries are not that big anymore. So in x86, when you have large pages, you don't really have to use 2 levels of indirection. So you have the directory, which is 10 bits. You append it to the offset. You append the page table entry to the offset to get the physical address, which for each of the physical page is 4 megabytes. Physical frame is 4 megabytes. And here is the mapping of the x86 page table entries. This is one of the example of one of the mapping. And this is the format of what each of the bit position are used for. Some of them are actually used for access control. Some of them are, for example, the user/supervisor bits. Those are used for access control, which I will go over that on the next lecture. And then here's what x86 defined for each of the page directory entry. 0 and 1 is whether this entry is present or not. If it's not present, you have to grab the data somewhere on the disk. Read or write, and then user supervisor, these are access control. And there are other bits for optimization, for example, whether the page level cache is disabled. And here, what did you have 64-bit address space? Now you can access a lot more data, and your linear address space, which each of the program sees, are now much, much bigger. So what's happening here is you have 4-level indirection. First of all, you have a first-level indirection, access the index into the page directory table that points to another page directory. Over here to here, you append that information to the actual page table to get the page table entry, append it to the offset, and then, prepend it to the offset to get the actual physical address. And as you can see, it is more or less linear process. So the OS or the software have to perform some management or optimization to make sure you do this efficiently. And one technique is to use TLB. I'll go over that on the next lecture. And it's like another excerpt from the x86. You can read that later after the slide if you want to get more information, including how this access, each of the bits that, in addition to just the typical physical address or the physical actual data that we would like to use to index to the next level, is used for the page table entry and the page directory entry in x86. And that's all in terms of the material today. Let me go over some sample problems. I just pulled it up like a few minutes ago. Here is a sample problem from 2013. Wait, where's my mouse? Okay. All right, and you can take a look at this information. I'm going to ask you the actual question. Let me make sure I got the same thing open up here. Okay. Okay. First of all, how many bits are needed for the virtual address space? The virtual address space, not just the indexes.
20 bits.
20? Let me look at the number. Yes. What about the physical address space? Let me write the answer along the way so that if anyone take notes, they can work on it too. Virtual address space. So it's 20 bits, and the physical. Wait, how many bits?
18.
Yeah, 18. How about how many bit is the page page table offset? Yes, 12. It's pretty much the log base 2 of those three numbers. When you're actually doing the question, make sure you use that correct number because this is the total bits you need.
Can we answer in log base 2 on the
If-
1 megabyte divided by log base 2.
Okay, that's a way. 2 to the 10 is kilobytes. 2 to the 20 is megabytes.
Okay.
Yeah, so 2 to the 30 would be another order, gigabyte. So you can use that to get the actual number. We will probably give some credit if you use log base 2. I'm not gonna promise you that you get full credit because I'm not sure how the rubric is gonna work out. But if you can work out the actual number and it's divisible by 2, I mean, if want to have the log of that number and it's like a number, not it's an integer. Sorry. You should be able to get that number, and we cannot expect you to get that full bits. And you will probably need to use that information later. So you probably need to use this number 20, 18, and 12 later.
Is it important to also know whether the memory is byte addressable or bit addressable?
For this particular case,
Yes.
I
Right, because if you're bit addressable, you have to represent all of the bits. But if it's byte addressable, you only have to represent.
So that information can be important depending on how we frame the question, because in the end, what these numbers for is for indexing. If you need that fine grain indices, you need those additional bits. If not, you will not.
Yeah, but that would change the
But
answer to this
yeah,
question.
if it's byte addressable, depending on how you access that particular bytes, right? Because sometimes it's specified in ISA that you don't have to specify the address that you specified is in a word, and then you have some information on which bytes in that particular word you want to access to. And in general, if we do not specify anything by default, it's word addressable.
Word addressable.
Yeah. All right. The next question, and use this information. I'm gonna write the question down. Get me the VPN and the physical address, given this information, and the virtual address is 15 to 13, just because they exist in this table. Okay. Virtual address is 15OX. And I'll write the actual bit field for in binary for that number. It's 101010. Okay, that's the binary representation of this number. The rest are zeros in the front. So this is not 32 bits. You just have to prepend zeros.
Yeah, zeros on there.
Just prepend the zero before it. It's all like zero.
Set the total bits if you're pulling out like specific numbers of bits.
That's true. Let me check. Maybe I got it wrong. Yeah, so 1 and 5, and this 2, 1, 3. Yeah.
No, it's just looking, sorry.
Yeah. I mean, that's one of the techniques that you can translate hex to binary easily. Just divide everything into 4-bit chunk and then just translate each individual of these entries into binary.
How are you supposed to use the TLB?
Right now, let's assume this. Actually, that's true. You will have to use a TLB in this case. Yeah. All right. Okay, that's not the ideal practice question, but since you guys took 13 before,
Could you do the first part then?
okay. I'm gonna give the TLB index and TLB tag. TLB index would be 0x2, and then the TLB tag is 0x45.
How does that work?
Okay, so TLB tell you whether you have a page. One thing you can use for the TLB is given the tag and index, you get the physical page number and check whether it's valid or not.
But you said the index is 2
Yes,
and the tag is 5.
That's a-
It's not in 2.
it's page fault.
Oh.
Yeah, but then even though it's page fault, you can get the physical address.
Well, you have to go to this.
You go to this.
So that we can't like.
Oh,
Because what's the. Well, the disk has to tell you. Like, you have to load the.
you can get that, I believe, in the page table for this problem.
Oh, you don't go to disk, you go to. No, I thought-
You refer to the page table. Okay, it's not a page fault, my bad, but it's a miss in the TLB entry. Yeah.
Okay. Oh, there you go.
So you cannot use the TLB to get the physical page number, but you can walk the page table to get the physical address. All right, sorry, I was computing too fast. So the hint here is which bits of these things.
So the top two, or the top group, top two
Do,
next,
do, do.
because
Yeah.
are
Yes.
the bottom 12 are the offset.
Yes, so these are the offset. So for the physical address, you can just use this 230 number to be offset. So it's 0010, 0001, 0011. So these number are the offset. And then you have to grab the rest of the information using the rest, 15. In binary. Yeah.
So it's 1, 5.
So which entry is this?
Maybe 1, 5. Over there. The one that says that the PPN is 1B.
This one.
No, 1, 5.
Oh, okay. Yeah, 15. Yes, 1B. It's 15 in binary, so yeah, it's not 0. Yes, so it should be 1B. And that is, okay, B, A, B, 10 to 11. 8, 10, 11, yeah. And these are all zeros. So yeah, that's the physical address for this particular case. I mean, do you want to do what if you hit in the TLB? I mean, we can do that, but I'll go over TLB in the next lecture. Oh, I guess since we have it here, why not? What if these bits are 0, 1? So this becomes 0, 0, 0, 0, 1. And let's assume, because I haven't really gone over TLB yet, the index would be index 2, 0x2 and 0x1f, if I got it correctly. Yeah. Now it's a TLB hit.
PPN on the TLB.
Yep. So it's 1f. If this particular index is valid, a lot simpler. Now you have 0, 1, followed by the page offset. Everything is easy. You just look at the TLB, append the offset. You don't even have to access the page table. So in the second case, you have 0, 1, and then this, 0x. And that's the answer. So as you can see here, if you have a TLB, which you can store it anywhere in the memory, what if you have them in the cache? You can access them really fast. And then, because you have information on what's the physical page number, you just grab that number, append it with the page offset, and you get the physical address. Now you skip the whole process of walking the page table, which can be longer, and then just grab that data in the physical memory. So I'm going to explain TLB in a much more details on how you get the indices and also the tag in the next lecture. Yeah.
If you had directories and just many more layers, would the TLB always point to the PPN, or would it just point to the next
So
layer of indirection, which would be more efficient, I guess?
that's a trade-off over there, because first of all, if you have more level of entries, it means that you have many more pages, right? Your virtual address is huge. If you point in the TLB entry, you point the physical page number, which most of the case it is, you have to have a bigger TLB. And the definition of how big this is doesn't really depending on the size of your virtual memory. It depends on what the system designer would like the TLB entry to be. Depending on the workload you're running, depending on your machine, what's the size of the physical memory, and what's the latency you need to access those physical memory as well as access the disk. So the bigger TLB, you waste some of the cache, because these things typically are being stored in the cache because those are fast and you can grab them really quickly in order to get the physical address. But cache is a lot more expensive because they are SRAM cell, not DRAM. And a few megabytes of cache would cost a lot more money. But if you store the PPN only, it's easy. You can just grab the PPN, get the actual physical address in DRAM. If you have another level, then you have to access DRAM in order to grab that page table entry, in order to grab the physical address. So you have one additional memory request. There's a trade-off there. Depending on how you design it, most of the case, TLB store the PPN in order to make sure you optimize for latency. And I mean, when you have the physical address, sometimes it's actually hidden in the cache, so you don't have to access the memory. Because data in the physical address space, sometimes they are stored in the cache. So pretty much you access the cache and you access the cache again in order to grab that data. You don't have to actually go to the memory at all. Like what if you have another indirection in the TLB, then you have to maybe access the memory and then access the cache. Now you have incur a much longer latency. Yeah. Any other questions? Right. So today we went over some functionalities of the virtual memory and how to translate the virtual memory to the virtual address to the physical address, and go over some practice questions. Next time I'm going to go over how TLB works. Also, what are the security and also permission access control that virtual memory can allow you to be able to do, and also have another practice question with a multi-level page table so you can get some more practice. And hopefully that helps you guys understand virtual memory some more. And if you have any question, including questions that you already have from 213, feel free to ask them on Piazza and we'll answer any of your questions. Right? And make sure you work on pipelining. It's a long lab. At least make sure you get the design up and figure out whether you have a bug or not.